So how can similar triangles be created by drawing lines through a triangle? Well, that is something that we're going to look at as we talk about using triangle similarity theorems. So we want to complete the steps to prove theorems involving similar triangles, and we want to solve unknown measures of similar triangles using the side splitter theorem. Now, your side splitter theorem, that is going to tell us that we have, if a parallel line to one side of a triangle intersects the other two sides, then it divides it into two sides proportionally. And we'll look more into that. And then, and of course, the converse, and the converse being that, yeah, if two sides are divided proportionally by a line, then it's parallel to the other line. And then solve for unknown measures of similar triangles using the triangle mid-segment theorem, and we'll talk about that too. And then, of course, the midpoint's going to be halfway between two halfway between 2 points, or the midway of a segment. So here we want to first make sure that we understand that our similarity theorems, we have angle, we have side, and then we have side, angle, side. So angle, of course, we have two triangles, and two of the angles are the same. Sides, of course, we're going to have two triangles where, all three sides are going to be congruent. And then the side, angle, side, goodness, don't mind my poor drawing of triangles. The side, angle, side. So those are just some of the similarity theorems that we have used. And then, of course, going into that side splitter, right? If a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. So what this is telling us here is the red line that has been drawn connecting DE, or in this case you could call that line DE, that's telling me then that segment AB is going to be parallel to line DE. And if that's the case, then we know that AD, the proportion, AD, the ratio AD over DC is going to be, so we have AD over DC is going to be proportional to BE over EC. And that is your side splitter theorem. And to prove that, well, let's see here. If we were to name a couple of angles, we'll call this 1, 3, 2, and 4. And let's see, we know that for triangle ABC, clean up a little bit here. We know that for triangle ABC, we have triangle ABC, and then we have AB is parallel to DE, here, parallel. And then we know that angle 1 and angle 3 should be corresponding angles. Angle 1 and angle 3 should be corresponding angles. The definition of corresponding angle, two parallel lines with a transversal. And then angles 2 and 4 should also be corresponding angles for the same reason. So then we know that angle 1 is congruent to angle 3 and angle 2 is congruent to angle 4. So that tells me then that if that's the case, then triangle ABC is going to be similar to triangle DEC, because I have angle, 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 angle. So they would be similar for angle, angle. So let's see, let's just write that down so we don't forget. I got ABC is similar to triangle DEC because of angle, angle similarity. All right, so then we know then that by the definition of similar triangles, I know this. The ratio of AD over DC is equal to the ratio of BC over EC, and that is the definition of similar triangles. I know that AC is going to be equal to AD plus DC, and I know that BC is going to be equal to BE plus EC, right? This is equal to the two smaller pieces put together. This is equal to the two smaller segments put together, right here. Now, and we do that because that's the segment addition, right? Segment addition postulate. It makes sense, you know, two little pieces put together make the big piece. And then, you know, I'm just going through the process, and we find that, you know, when we look at this, we could do some substitution properties. But I've just been able to sort of identify some of the characteristics going on in the side splitter. So ultimately, we will end up coming back to this right here, that those ratios are going to be equivalent. AD over AC is equal to BE over EC. Let's see here. So expected to. Looking at this in practice, so I have triangle HYB and triangle AYB are, well, let's see. Again, AYB and HYB, they are going to be similar because I have angle, angle similarity. So we are looking at they are going to be similar by the angle, angle similarity. And what is the value of X? Well, we know, given some of the stuff that we were just talking about, I know that YB let's see here. The ratio of trying to get started. So I have the ratio of HA over AY is going to be equal to BV over YB. And then if I do some substitution, that means HA is going to be X minus 17 all over AY, which is 17, and that is going to equal 22 divided by 16. And I'm going to go ahead and do my cross multiplying here. And I'm going to end up with 16 times X minus 17 equals 22 times 17, which is going to be 16X. Okay, that's going to be 16X minus 272 equals 374. So if I add 272 to both sides, I have 16X is going to be equal to 646 divided by 16, and goodness, I hope X is going to be equal to, I'm going to go ahead and get the calculator out, just because I'm feeling lazy. X is going to be equal to 40.375. So that is the length. So it looks like HY is going to be equal to 40.375 5. So that's using my side splitter information. So, of course, what was the hard part? The ratio of this segment over this segment. Well, this segment was 17, but we know that the entire length would, this segment right here is the entire length minus that 17. So that's how we came up with x minus 17. And more examples than all right. So let's see here, finding the value of x and the distance between t and e. So again, the same thing's going to apply here. We know that the ratio of this, okay, let me change that. I should be able to tell that if this angle and this angle are equal, this angle and this angle are congruent, let me use those good geometry terms, then that tells me that these are going to be parallel. Now, if those are parallel, of course, we're going to be able to do angle-angle similarity just like before. And in doing so, I know that the ratio of this segment over this segment is going to be equal to the ratio of this segment over this segment. So I will just say that FC over CV is going to be equal to TE over EV, and they are asking me to find the distance here between this one right there. So I don't know that, that's X, but I do know that FC is 6, CV is 10, TE is going to be X, and then EV is going to be 15 minus X. So if I do my cross multiplication, I'm going to end up with 6 times 15 minus X equals 10 times X, or this is going to be 80 minus 6X equals 10X. Add 6X to both sides, and then I'm going to end up with 80 is equal to 16X dividing by the coefficient, and then X is going to be equal to 5. Goodness, does that seem right? It really doesn't seem right, and it messed up right here. I did not use the distributive property properly, so let me go back here and fix my mistakes. Right, we all make mistakes, and that's why we check our work, and it did not seem correct. So here, let me redo that. 6 times 15 is not 80, that is going to be 90 minus 6X equals 10X, and again going to add 6X to both sides. So I'm going to have 16X is going to be equal to 90, divide both sides by the coefficient, and then X is going to be equal to nope, not 4, 5.625. So there you go, X is equal to 5.625, which happens to be the length of TE. TE is going to be equal to 5.625. So let's see here, we could probably, okay, so using the triangle similarity theorems, we are able to complete the steps to prove theorems involving similar triangles, and then solve for unknown measures of similar triangles using the side splitter theorem and its converse, and then solve for unknown measures of similar triangles using the triangle mid-segment theorem. And the triangle mid-segment theorem is the mid-segment of two sides of a triangle is parallel to the third side and is half as long. So the mid-segment, if I have a point here, and they are both mid-segment points, we'll call that E, D, A, B, C, and I have a line from mid-segment to mid-segment, then that is going to make this line parallel to this line. So again, the midsegment of two sides of a triangle, these are midsegments because they're equal, it cuts it in half. This is the midsegment of this AC. So this line right here is going to be parallel to the third side. So, and we will be able to apply that midsegment theorem. So if I have, all right, so using the midsegment theorem, I should be able to look at this diagram and pull out some stuff. I should be able to say that, well, it looks like point O is a midsegment of ED, and point N is a midsegment of EF, and point M is going to be a midsegment of DF. And so if I have, let's just go with this. What is DM? All right, so I'm looking for this length right here. Well, I know that according to the midsegment theorem that ON is equal to 1/2 of DF. So if ON is equal to 1/2 of DF, that means that ON is equal to DM plus MF, or actually, ON is equal to DM, and, they're all congruent statements because M is a midpoint, so that makes DM, the measurement of DM is going to be equal to the measurement of ON, which is going to be equal to the measurement of MF, just because of the midsegment theorem. So if ON is half of DF, that means that DM is going to be 38 and MF is going to be 38. If I were to plug in these other segments, which aren't there right now, I would know, just without doing that, I would also be able to look at and say, if this O is a midpoint of DE, then if OE is 22, that means DO should also be 22. If EN is 30 and N is a midpoint, then NF should also be 30. And then if, right here, MN is 1/2 of ED, which is going to be 22, and OM is 1/2 of EF, which is going to be 30. So I'm actually able to label all of these things using that principle, knowing that this segment is 1/2 this segment. So what is the measurement of DM? Well, we turned out to find out that the measurement of DM was going to be 38 units. So again, that is just us being able to apply some of the basic information from the midsegment theorem. And then finally, let's do one more right here. And I'm going to have this thing. It's going to be point S, point T. I'm going to call that one H. This one G, this one F. If HT and TF are congruent, that makes point T is a midpoint. And then if SH and SG are congruent, that makes point S also a midpoint. And we know because of the midpoint that it looks like ST is going to be equal to 1/2 of GF. And if ST is 8, what is GF? Well, GF is going to be, let's just say 8 is equal to 1/2 GF. Go ahead and multiply by the inverse there. So 16 is equal to GF. So we're looking at 16 using that midpoint theorem. And there you go. Again, all of these things just start working together and being common, and that ties directly into the ratios that we were working with at the beginning of this section. So with a little bit of practice, these things will be a piece of cake. You can see that the algebra is very light, so just knowing what the words are.